Hello everyone, myself Dr. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the course Computer-Oriented Statistical Methods. And today's session is on Markov chains and transition probability matrix, TPM. In the last session, we have discussed about what is a stochastic process, and different types of stochastic processes, classification. In that, we have discussed about a discrete stochastic process and continuous stochastic process. And today, we are going to discuss about Markov process and Markov chains and TPM, the transition probability matrix. Now, what is a stochastic process? Simply, in the last session, we have discussed about stochastic process, any system or process that varies with respect to time. So here, a stochastic process is a mathematical model for describing an empirical process that changes in time according to some probabilistic forces. So we can define stochastic process as a mathematical model for describing an empirical process that changes in time according to some probabilistic forces. Now, there are some important stochastic processes which are Markov chains or Markov processes, counting process, in that Poisson process, and then birth and death processes. And coming to this Markov process or Markov chains, a Russian mathematician Markov defined and investigated a particular class of stochastic processes which are known as Markov processes or Markov chains. And the Markovian property, for example, the present state is known to us and the conditional probability of the next state is independent of the states prior to the present state. So, the conditional probability of the next state is independent of the states prior to the present state. For example, we have, this is the present one, xt, the future one or the next one is xt plus 1, and previous ones are xt minus 1, xt minus 2 and so on. So, the probability of the future state depends only on the present state. It is independent of the previous states of the present state. So, I can denote xt as I, which is the present state at time t, xt plus 1 by j, the future state or the next state t plus 1. Now, the conditional probability statement of Markovian property is given by the probability of the future state, which is j, in which x0 is k0, x1 is k1 and so on, xt is I. This is the last one. So, this is the future state, means this is the present, and these are the states prior to the present one. So, this probability depends only on the present. So, that is xt plus 1 is equal to j, that depends only on xt equal to I. So, for t 0, 1 and so on, and for all possible sequences. That means, what is the interpretation here? Given the present, the past is irrelevant in determining the future. If we have the present value, the past values are irrelevant in determining the future. We don't need the previous values or the past values. The Markov process. A stochastic process is said to be Markov process if for a given value of x of t, the value of x of v, where v is greater than t, that means v is greater than t means that is in the future state. This doesn't depend on x of u, where u is less than t, so the previous value. Simply, that is, the future behavior of the process depends only on the present value, but not on the past values. The same thing can be stated as how the process arrives at the current state is irrelevant. How the process arrives at the present state is irrelevant. We need only the present value. The same statement can also be stated as a stochastic process has the Markov property if its future evaluation depends only on the current position but not on how it got there. So that means how it reached there. And coming to the Markov chain, let us consider a sequence of states x1, x2 and so on xn. We can denote the states by this or else e1, e2. So these states are nothing but the random variables. These are random variables or the outcome simply. So let us consider a sequence of states, and it is a Markov chain if each xn is a random variable and if the probability of future one depends only on the probability of present one, that is equal to P of xn equal to n, where xn is small xn. So there are some important points to be discussed on the Markov chain. So consider the states E1, E2, etc. En. Just now I told we can denote the events by capital letters. So consider the states E1, E2, etc. En. Assume that the probability of system being in a given state at next trial depends only on its present state but not upon the states it may have been earlier times. Simply the future value depends only on the present value. So if at any time the system is in state Ei, the probability of the system being in the state Ej. So from Ei to Ej transition with the probability Pij. So this Pij is called the transition probability and this process is called Markovian process. So from state Ei to Ej, the probability is Pij. The outcomes Ej are called states of Markov chain, and at two successive trials, for example say nth trial and n plus 1th trial, the conditional probability is Pij. Just now we discussed from Ei to Ej or Ei to Ei plus 1. So that is the probability of transition from the state nth trial to the state n plus 1th trial. So nth trial to n plus 1th trial. In nth trial, for example, the state is I, and n plus 1th trial, if the state is j, from I to j, the probability is denoted by Pij, given by Pij, and that Pij is called one step or unit step transition probability, because the transition is from one state to another state, only one step transmission. So Pij is called one step or unit step transition probability. Similarly, for example, two states, if we are moving from I to j and then j to k, then it is two state transmission. Similarly, n states or m states also we can define. So Pij power m is called m step transition probability. M steps transition probability. The next topic is transition probability matrix. Just now we discussed from a state Ei to Ej, the transition with the probability Pij has been occurred. So simply, if we arrange all such probabilities, transition probabilities in a matrix, that matrix is called a transition probability matrix. In shortcut we use TPM. The matrix formed by the transition probabilities Pij is called transition probability matrix. Let us consider a stochastic process and n states. Then let us find all the Pij's, the transition probabilities. So since there are n states, here E1, E2 and so on, E3 and so on, En. Similarly here E1, E2, E3 and so on, En. Now P11 is the transition probability from the E1 stage to E1. P12, E1 to E2, P13, E1 to E3, P21, E2 to E1 and so on. So simply a matrix formed by the transition probabilities is called transition probability matrix. Now the characteristics of a transition probability matrix. In a transition probability matrix, all the elements must be positive, or we can say greater than or equal to 0, so non-negative. All the elements must be non-negative, and the elements lies between 0 and 1. This is obvious because we are writing the probabilities as elements. We know that the probability lies between 0 and 1. Hence, all the elements lies between 0 must be between 0 and 1, including 0 and including 1. So, all the elements of a transition probability matrix must be non-negative. And another important point is the matrix must be a square matrix, n by n matrix. For example, 2 by 2, 3 by 3 and so on. So, the first point, the order of the matrix must be n by n. That means a transition probability matrix must be a square matrix. Second, all the elements must be non-negative, must be between 0 and 1, and along any row the sum is equal to 1. If you add the sum of the elements of a particular row, you should get 1. Now, as an example, let us check whether the following matrices are transition probability matrices or not. That means the following matrices represent a stochastic process or not. So, do the following matrices represent a stochastic process? To represent a stochastic process, these matrices must be transition probability matrices. Let us check the previous 3 conditions. It must be a square matrix and all the values must be non-negative and must be between 0 and 1. And also, along any row, the sum of the elements must be equal to 1, unity. Now, consider the first one. Here it is a 2 by 2 matrix, a square matrix. First condition satisfied. Second, all the elements are non-negative, there is no negative element. And third, along any row, along the first row, the elements are 0 and 1, total is 1. Along the second row, 1. So, it is a transition probability matrix. Hence, it represent a stochastic process. Coming to the second, again the same, there are no negative elements, all are non-negative, and it is a square matrix, and along each row the total is 1. So, it is a transition probability matrix which represents a stochastic process. Now, coming to the third one, yeah, of course, here 1, 2, 3, 3 rows but 4 columns. So, 3 by 4, which is a rectangular matrix. It is a rectangular matrix. A transition matrix must be a square matrix. So, first condition itself fails. So, it is not a TPM and hence it does not represent a stochastic process. Coming to the third one, again it is a 3 by 3 matrix and along each row 0 plus 1 by 2 plus 1 by 2, which is 1, and here 1 by 2 plus 1 by 2 plus 0 again 1, and 0 plus 0 plus 1 again 1. So, it is a transition probability matrix and hence it represents a stochastic process. And the last one, yeah, of course, it is a 4 by 4 matrix, it is a square matrix and all the elements are non-negative. But you can see here the total is 1, here half plus half 1, here 1 by 4 plus 1 by 4, which is 1 by 2, again plus 1 by 2, 1. So, total is 1. But here the LCM is 16, 5 plus 7, 12, 14, 15 by 16, which is not equal to 1. Hence, it is not a transition probability matrix and it does not represent a stochastic process. Like this, we can check whether the given matrix represent a stochastic process or not. For that, we need to check whether the given matrix is transition probability matrix or not. And a transition probability matrix must be a square matrix and all the elements must be non-negative and must be between 0 and 1. And the last condition is sum of all the elements in any row must be unity. And there are some properties on the transition probability matrix. If there are 2 matrices P and Q both represent a stochastic process, then if you multiply these 2 matrices, the multiplication of 2 matrices PQ is also a stochastic process. That means PQ is also a transition probability matrix. Similarly, P power M is also a stochastic matrix. So, in today's session, we have discussed about the Markov process or Markov chain and transition probability matrix. And what is the transition probability matrix and what are the characteristics and some examples also we have discussed. In the next session, again we continue the same. We introduce the regular and irregular stochastic processes and some problems on regular and irregular and Markov chains also. So this is for today's session, and we'll meet in the next session. Thank you.